reaction we use the catalyst as a quencher and add the both component of the grease system. The grease system is contain reagent A and B. So this is the end production, the oxidation of hydroxamide. A methanoglobin, when react with the H2O2, it forms the oxyferrite species, and that species is combined with the hydroxamide and produce oxidation products, and methanoglobin is regenerated. To detect that oxidation products, we use the grease reagents.
Ishita, could you go back to the previous one?
Yes.
Okay. So this is the reaction that takes place, right?
Yes.
Okay. So what do you have in? You have three different components, right?
Yes. First we add methanoglobin, and then we add when H2O2, then it forms the oxyferrite compound. And over there, when we add hydroxamides, at that time it produces nitrite, which is as an oxidation product, and then methanoglobin is regenerated into the reaction. As the concentration of the H2O2 is more, 5 millimolar, so we use catalyst to stop that reaction.
Let's go to the next slide. What happened to the hydroxamide in this reaction?
The hydroxamide is converted into the oxidation product like NO, nitrite.
It releases NO.
Yes,
right? Okay.
nitrite.
So it gets depleted.
Depleted,
right.
Yes.
What happens to the H2O2?
The H2O2 is converted in regenerated methanoglobin again.
Right. So it regenerates the myoglobin, right? Or generating the higher oxidation state of the of myoglobin. So it also gets depleted. What about the myoglobin?
The myoglobin is remain the same.
The concentration remains the same. So it's catalytic.
Yes,
okay.
catalytic.
So now let's look at the concentrations. Okay. So that's why the concentration of the myoglobin is very low, right? You don't need a lot of it. Okay.
Yeah.
Whereas the H2O2
is in more amounts.
Right. So it has to be in excess. Okay. Now, how do we determine which concentration do we want to use here? For example, how can one determine, or how did you determine that 10 micromolar of myoglobin is enough or not enough? What's the limitation?
Yeah, because I tried with the lower concentration too.
And what happened?
But the rate of the NO production, it's not showing. The absorbance was not clear.
Right.
So we cannot detect the lower. If the methanoglobin is lower than 10 micromolar, then we cannot detect the NO production.
Correct. So the limitation was the limitation of your instrument detection.
Yes, detection.
Right. Now, if you were using a different instrument, you may have been able to do it, right?
Yeah, may or may not.
Because what was different between the two instruments?
Because the diode, the path length is more like as a 10, and I'm using the nanodrop spectrophotometer. It has a path length of 1, so that's the
1
difference.
millimeter versus 10 millimeter. So
yes.
It's a factor of 10.
10.
Right.
And so for the this is the grease reaction to determine the oxidation products, which is nitrite. The sulfanilamide is a solution A of the grease reagent, and NADD, which is called N1-naphthyl ethylene diamine dihydrochloride, which is the solution B of the grease reagent. When nitrite is react with the sulfanilamide, converts into the diazone, and then when it react with the NADD, produce the azodine, which we can measure at 540 nanometers. So to begin with the experiment, we need to know that how long we have to wait for the color development. And for that, we did this assay on the diode array using sodium nitrite and grease reagent. So we can see from the figure that after 20 minutes, the graph is, the color reaches the plateau level. So in each and every reaction, I will wait for 20 minutes. And the standard curve for the grease reagent, over here I use a different concentration from the stock solution of sodium nitrite, smaller as 20 micromolar to the 250, and I find the extinction coefficient of 0.0051, and error bar is plus or minus 0.0002. Over here, how reproducible are the measurement of the nanodrop spectrophotometer? That we can answer from here. You can see over here the slope of the hydroxamic acid. I tried 4 different compounds. The one is acetohydroxamic acid, and then benzohydroxamic acid, hydroxyurea, and the SAHA. you can see the slope are similar. So we can say that nanodrop, the result obtained from the nanodrop is reproducible, and it has an error, but it's not larger than 5%. We can say that.
Okay. But before you even did this experiment, when you just approached the nanodrop to begin with, you tested it even
with the control, yes,
right?
with the control, and with the 100 micromolar concentration. Because when I use 200, it's too big, and when I use lower, then it's not showing anything. So I try with the 100 micromolar concentration, and I did the same thing. I try like 2 times, 3 times, and like 30 minutes the same thing, and it gives me the same absorbance. It's not like exactly same, but it gives me difference of 0.05 or something. It's not more than that.
Right. So actually it gave you, so that was the first step to
yes,
just to see how reproducible it is when you just use a known concentration.
Yes.
That should
so I tested with the control as well as one with the sample too.
Right. And the error there was less than 5%.
Less than 5%.
Right? And here it's about 5%,
yes.
right? It was much smaller than 5%. And the reason is because here you have more.
I did like 4, and these are average of 4 trials actually.
Right.
Those 4 is average of 4. So
right. But if you go back, this 5% represents not just the error of the instrument. It represents all the errors in your experiment.
Together,
it represents
yes.
your pipetting error, fluctuation in the errors in the concentration.
Maybe the drop.
Right,
everything.
In the pipetting and in the measurements. So that tells you that the overall
this is
accuracy of your work was good, because your error is, you can't expect to get anything less than 5%. So really, that means that you really did a good job in that.
Thanks. And is this the best way to analyze the small sample of how to obtain the chemicals? Yes, because with the nanodrop we have to use just 1 drop. So if it's 200 microliter, we have solution, we can measure 10 times, so we have 10 points. So it's the best way. And if the sample is expensive, we can use with the small small amount. Here are the results. The results are showing the one with acetohydroxamic acid I showed you, the benzyl hydroxamic acid, hydroxyurea, SAHA, and this is the overall from the 4 of the compound, the average from the 4. From here you can see the nitric oxide production as a function of time. The hydroxyurea produced more NO, and the SAHA is produced the lowest amount of NO. This is NO release rate for the hydrocolloid compound use. The NO production rate have error bars of plus or minus 0.002 micromolar per minute. You can see for hydroxyurea is 3.09 micromolar per minute, and for benzohydroxamic acid it's 1.91. Acetohydroxamic acid is 1.08, and for the SAHA is 0.882 micromolar per minute. What are the structural and chemical features of the different HPCs make this rate different? Over here, you see hydroxyurea has a fast state NO release. You see over here the hydroxyurea has the smallest structure. So the smallest the compound is the higher the NO production, and the larger the molecule will have a slower the oxidation rate. The hydroxamide has to make a contact with the heme group inside the myoglobin. The smaller molecule get easy access to that heme molecule. So the conclusion is the SAHA has the slowest NO release rate, and not the NO production is not the primary function of the SAHA. The primary function, we can conclude that as the histone deacetylase inhibition. The relatively slow NO release rate means that the SAHA is more resistant to oxidation. So it is a long-lasting drug, so we can give a few doses, not too frequent doses. You can use like 1 or 2 doses for the cancer patient. And thank you everybody, and all Professor Samoni, Jorge, and even Dr. Capita, and this is not here. I'm thankful to him. So